Good evening. Last summer and autumn, the giant planet Jupiter was on view in the evening sky. And this is a sketch I made of it with my 15-inch reflector. You can see there the yellowish flattened disk and the famous cloud belts. It wasn't really ideally placed. It was low down in the sky, but it was very bright. And in fact, Jupiter is brighter than any other planet, with the exception of Venus. We've now lost it in the evening twilight, but all the same, we're in for some very exciting times. Now, Jupiter, remember, is large, far larger than the Earth, as you can see here. Its diameter is nearly 90,000 miles. You can fit 1,000 Earths inside Jupiter and still leave room to spare. But Jupiter is not a world with the same kinds as the Earth. It's not solid and rocky as we are. There is, in fact, a hot silicate core with a temperature of at least 30,000 degrees, possibly rather more than that. And around it, there are layers of liquid. Not water, but liquid hydrogen. First of all, metallic hydrogen, and then molecular hydrogen. And above that come the cloud layers we can actually see. And those cloud layers are always changing. Jupiter's a world of constant surprises. You get the main belts, you can see them there, the North Equatorial and South Equatorial, the bright zones, and wisps and spots and festoons, and those clouds are in constant motion. Jupiter's a world in constant turmoil, and there are tremendous winds there. And that strange feature also, the Great Red Spot, a whirling storm that's been on observation most of the time since the 17th century, and it can have a surface area greater than that of the Earth. We are not sure about the cause of the colour. It may be due to phosphorus, but certainly the red spot is there, and it's always well worth looking at. Now, Jupiter has a very long ear, nearly 12 times as long as ours, after it's nearly 500 million miles from the Sun. But it has a very short day. It's a quick spinner. And on Jupiter, the day is less than 10 hours long. And the equatorial part goes around the quickest. That means if you look at Jupiter through a telescope, even after a period of a few minutes, you can see the markings being carried very slowly from one side of the disk to the other by virtue of the planet's rotation. And there's a strong equatorial current there, and there the rotation period is only on average about 9 hours 51 minutes. So far, 6 spacecraft have been past Jupiter. In the 1970s, we had the 2 Pioneers, and then the magnificent Voyagers. And Voyager 1 swooped by Jupiter at a distance of only 200,000 miles and sent back superb pictures of the planet. It also surveyed the satellite system, and Jupiter has an extensive satellite family, and 4 members are big. And here we see a mosaic of Voyager pictures. There down in the right-hand side, we see part of the icy crater satellite Callisto, a bit bigger than our moon. Then to the lower left, Ganymede, over 3,000 miles across, and actually bigger than the planet Mercury. Then between that and Jupiter, we see the icy, smooth satellite Europa, and then right in the background, the strange volcanic satellite Io, just a bit bigger than our moon, and in fact a world where there's constant volcanic action going on, the most active world we know, and that was totally unexpected. So far as the clouds are concerned, obviously we can only see the top layers, but underneath we think there are definite layers of material. There's the Jovian stratosphere, below that the troposphere, and then we think layers of ammonia, ammonium hydrosulfide, and then probably a layer of water, or water ice, or water crystals. Of course, we can't see it, and therefore we had to depend upon probes going down and finding out for us. And we had a bit of hope for nature last year, because comet Shoemaker-Levy actually impacted Jupiter, and the bits of the comet plunged down below those clouds and left very obvious scars there, as you can see, and the results of that can still be seen. But even so, there was still a great deal we didn't know. And the next probe to hit Jupiter is going to be a man-made one, the Galileo probe. Now, Galileo was launched in 1989. It's made up of 2 parts, an orbiter and a lander. The orbiter is scheduled to go round and round Jupiter, monitoring again its satellites, and the entry probe was designed to go into Jupiter's clouds and send back information for possibly half, 3/4 of an hour before being destroyed. So it would send back information during the last few minutes of its life. I may say that Galileo has not had an easy history. One very important part of the communication system, the high-gain antenna, never has opened and won't open now. And secondly, as it neared Jupiter, there was trouble with the onboard tape recorder, and no one really knew whether Galileo was going to work or not. But on December the 7th, it did encounter Jupiter, and the information we have back now is that it really has succeeded. And at this stage, I'm delighted to be joined once again by one of our most regular and welcome visitors, Professor Gary Hunt. Welcome back, Gary.
Thank you, Patrick.
Well, what about Galileo?
A great success, Patrick. OK, it's taken 6 years to get there after 6 years delay and almost 20 years of work, but there's no doubt this has been a most marvellous success. I'm sure as the months go by, it will unfold a great deal of new scientific information, indeed understanding of Jupiter and its environment. Let's take you through this rather special flyby, because we got so used to Voyager and the quick route to the outer solar system, but here is an opportunity with Galileo, having been launched October '89, it had to get enough power to get itself into the outer solar system. After the launch, first step was to actually get some energy by flying by Venus, which it did in February 1990. That was the first time to build up a bit of energy, back past the Earth in December 1990, and then out into the asteroid belt. And it was doing science as it went. We looked at Gaspra in 1991. Here is an image of it, looking rather like, typical asteroid, perhaps looking like some of the major moons we saw, the 2 moons we saw around Mars.
Yes, definitely.
So I think that's some relationship we actually see. That was the first stop on its extra science. Back around the Earth again, and we can look back at the Earth picture. This was the last chance that Galileo would have of the place where it had started, but then it was gaining further energy back into the asteroid belt again to see Ida. But Ida was a surprise, because Ida is not, as you can see, alone.
Funny is the thing, Ida is something like 50 miles in diameter, because they're rather irregular in shape. And there, to the right-hand side of the screen, you can see a small dot. And that is Ida's satellite, now known as Dactyl, only about 1 mile across. And this is the first definite proof we had that asteroids can have satellites. And I think probably was not expected.
Well,
so it left Ida, and then en route for Jupiter, and more adventures.
I think the important thing here is all the way through the flyby and the whole cruise out of Jupiter, new science is being obtained. And I think some of the other interesting aspects were that the fact that Galileo itself has found and travelled through 2 very large dust clouds, one in June of last year and then one in August this year, which actually lasted 3 weeks, a long way from Jupiter. We're talking distances of 110 million miles from Jupiter, and a cloud that lasted quite a long while. Tiny fragments of material. You can think of it almost like that dust from a cigarette. But that's how fine it actually is. But we're talking about material moving at enormous speeds, 100,000, perhaps 500,000 miles per hour. Where does it come from? Well, some speculation could be that it's coming from Comet Shoemaker-Levy, or perhaps even from the Io itself and some of the volcanoes.
It was further away from Jupiter than expected, wasn't it?
A long way from Jupiter. We're talking about, say, if you want to measure it in Jupiter radii, we're talking about 2,400 Jupiter radii, a long way out. But the important thing is, out in the space between the planets, there's a lot of debris. Yes, we've seen it before with Ulysses. Probably Voyager would have found it as well, but only now the modern instruments are capable of actually detecting it. But then as the spacecraft moves on, it can start to encounter the Jupiter environment. Jupiter is a huge, giant magnet, a very hostile magnetic field. And the first time you get in contact with Jupiter is when you cross the bow shock. This particular picture is an illustration of what it looks like in general. The shape is always the same, like a huge windsock, but actual dimensions will vary according to the strength of the solar wind, and this particular picture is built up from our understanding with Voyager. The first indications of it came as early as November the 16th, when we in fact were as many as 200 Jupiter radii away, and then the bow shock was encountered many times, and on the 26th of November we were certainly inside the Jovian magnetosphere at a distance of about 125 Jupiter radii. And
of course inside Jupiter's dangerous radiation zones.
Yes, and I think then as you move in, you're going to get closer to the planet, closer to the satellites, and as the probe then was separated in July, on July the 13th, it really was almost like a paratrooper drifting on, aimed at this particular point on Jupiter, really then almost helpless. It was then focused on reaching the upper atmosphere, measuring lightning storms, measuring charged particles to its aiming point 6 degrees north into the clouds of Jupiter, near to, in fact, the junction between the equatorial zone and the north equatorial belt. You can see marked with the arrow exactly where the aiming point was, and this particular image from Hubble, if we go closer, you can actually see the spot where we expected the aiming point to be. This is a very turbulent area, huge convective storms, the white clouds, the blue areas, the red areas near it, maybe the downward motion. Very turbulent, highly dynamic changes. And this sequence of pictures show how the aiming point, how the clouds are changing rapidly in this particular time frame. We're slowing down from an enormous speed of over 100,000 miles an hour, retardation of more than 200 times the Earth's gravity, as it slows down, measuring the lightning, the charged particle environment, descending slowly through the clouds to provide us with our first understanding of what's beneath the mysterious clouds of Jupiter.
How long did signals come back?
Well, this is the measure of why we think we have a successful mission. We have the full data set. The first question was, could we get down to the water cloud levels? That's the first 40 minutes of data. Yes, we have that. That data's on the computer memory of the spacecraft. And then could we get down to 75 minutes of data? The answer, yes, we have. That's taken us even further down. Temperature like 400 Kelvin, 200 degrees centigrade, enormously high temperatures. Pressures probably 20, 30 bars maybe to be expected. In that measure of a perfect mission, the answer is yes.
How deep did it go?
Well, down, we think, beneath the water clouds, probably pressures as much as 20 or 30 bars level. So it's very deep down. And all the way down, as the probe descended, not only measuring lightning, the charged particle environment, we're anxious to find the hydrogen-helium ratio. That'll be one of the measurements we're taking. We want to know what the cloud particles are like. Are they solid? Are they liquid? What size are they? They will be measured. The heat structure of the atmosphere will be measured as well. So the details of the composition, the structure, the whole environment in that one location is important. The question, obviously, to ask is this representative of Jupiter? The answer is, well, you can see, looking at the profiles of Jupiter, here is one from Voyager, which can look at the location very close to where the probe descended. You can see how the temperature drops as you move towards the cloud tops coming through the stratosphere. You reach the tropopause, and then as you go deeper into the atmosphere, it gets hotter and hotter. Remember, as I said, this shows our level of knowledge down to a pressure of 5 bars. We've probably got to 20 or 30, so we're really in a new regime. If you look at another location on Jupiter, you see that there's not much difference in the overall structure, because it's just a turbulent, rapidly rotating planet. And then look at the red spot again. So yes, this is reasonably representative, but the important thing is we're showing here the data to the best of our knowledge from past missions. We've now gone to a totally new level.
Of course, the incoming pictures had to be sacrificed because of the faulty tape recorder. But we have got the data now, but you don't get the results back straight away as we did with Voyager.
It's a good, important part to emphasize, Patrick, that we will not get information immediately. Yes, this is not a pictorial gathering mission. That will take a long while to come. And because we're trying to get information deep into the atmosphere, and they're very important physical experiments, the instrument is going to be calibrated. The data is now back on the ground and being analysed. It will take some days to get it out. But if you look at the cloud structure, this will emphasise precisely the levels you've got to. Remember, Jupiter is colourful. There are reds, there are greens, there are browns, there are all sorts of whites and colours there as well. We've certainly got down into the ammonia clouds, and we're showing here levels like 70 kilometres below the cloud tops. We've probably got down to 90 or 100 below the water levels into the water ice levels. And we already know from last year with the Comet Shoemaker-Levy encounter, there were some spectacular surprises. That impact, a huge impact, threw up a lot of material. It confirmed the origin and presence of methane and ammonia. It showed that there was water there, but water in enormous amounts, probably 10 times more than we expected. And then the really surprising observation of the presence of carbon monoxide. So who knows what now will be found with the more detailed measurements, the first measurements in situ off the probe of Galileo as it descends into the clouds. This is a very exciting time.
Well, the entry probe has done its work, better than anyone could have expected, I think. And of course, the entry probe was now being destroyed. But that leaves the orbiter. And after the entry probe has been dispatched, the orbiter fired its motors and has been put into the correct closed path around the planet, where it'll go on scanning Jupiter itself for at least 2 years, and also, of course, imaging the satellites.
Well, the interesting thing about the mission from the orbiter point of view, we've already gained a bonus, because in flying in towards the planet, it made a much closer pass to Io. The original pass was going to be about 1,000 kilometres. They went as close as 550 kilometres. Fortunately for the spacecraft, there was very little radiation effects outside of Io, and although it built up inside Io, it doesn't seem to be any danger to the spacecraft. So by going closer to Io, what this in fact means that the whole series of orbits as we build up our knowledge is going to mean an earlier encounter of Ganymede, a week earlier in June 27th of next year. But over the next 2 years, a whole series of orbits will be centered around each one of these giant satellites. They're satellites to Jupiter. They'll be planets to anybody else. And they will build up almost a set of petals, so you can interact and investigate the environment around these bodies, their interaction with the magnetic field. Yes, you'll get some images far better than we've ever had from Voyager, but coupled with measurements of the chemistry of the surface, the chemical composition of their environments, which will improve our knowledge of the geology, their interaction, and indeed give us a whole new picture of what these bodies are like. And possibly, Patrick, we may even find some more satellites.
We may well do so, I think. And after all, the really dangerous one is the volcanic satellite Io.
That's a particularly interesting one, and one once we looked at with great detail. We were lucky on Voyager to find active volcanoes. Almost certainly we're going to find them again on Galileo. The interaction with the magnetic field and the torus as well that connects Io indeed to Jupiter will be something that will be studied continuously. To be there not as a snapshot and a quick flyby as we had with Voyager and earlier missions, but to be there over a period of 2 years, and to be able to couple it with measurements from Hubble and observations too, we'll be able to build up the timeline and increase our knowledge of the temporal and spatial variations.
There's one, of course, important point here. Galileo has just encountered Jupiter in 1995, but it was planned in the 1970s, so the onboard material is old.
I think that's the important part that we reflect upon. We're talking here saying it's a success. I think the real success is a 6-year trip after a 6-year delay and almost 20 years of planning. So many of the instruments are designed and in fact utilizing some of the older technologies, but they're reliable, they're robust, they're trustworthy. And if we were coming about it today and developing instruments for future missions, perhaps we would have made things differently, and we'll have that chance in the future. But come what may, we have a very successful mission.
Well, the next far planet probe is going to be Cassini to Saturn, launched next year, we hope.
And I think the value here is that Jupiter is just one of the major objects in the solar system. A comparison with Saturn is important, but the probe we're having with Cassini is not just to Saturn, it's to Titan II. And then by the year 2004, we'll have a better picture of the planets, their satellites, and indeed what their atmospheres are really like.
Well, you know, Galileo's had many trials and tribulations, and I think right up to the last moment, no one was sure whether it was going to function or not. We haven't got all the results back yet. We won't get the pictures yet a while.
No, you won't. They will take time to come back. The mission is not a totally pictorial one, and over the next few months, material will be coming out, observations are coming out, and detailed analyses will be able to provide us real measurements of what's taking place. This is a deep scientific mission.
And just as a last word, Gary, do you expect that the pictures are going to be better than those sent back by Voyager?
Oh, much better in spatial resolution, and of course we have high spatial resolution and be able to study them for over 2 years. A tremendous opportunity.
Well, after all this time, I think it's fair to say now we can regard Galileo as a definite success. Would you agree on that one?
Absolutely, no doubt at all, and I look forward to seeing the observations and indeed what the analysis prove over the next few days.
Gary, thank you very much.
Thank you.
And since this is our last programme of 1995, I hope it's not too early for me to wish you all a very happy Christmas and New Year. And so, until 1996, good night.